What information does the modern periodic table provide? In the previous lesson, we learned that the position of an element in the modern periodic table is decided by its electronic configuration. The modern periodic table is a powerful source of information to the chemist. Can you now guess the information provided by the modern periodic table? The modern periodic table gives information about many other properties of an element. Recall that inert gases were discovered late because they are very unreactive and their compounds are not formed easily. But why is that inert gases do not react with other elements? Why are inert gases so unreactive? Observe the number of electrons in the outermost shell, valence shell. In both the cases, there are 8 electrons, that is, the outermost shell is completely occupied or full, 2n square. What will you do if you are offered sweets after you have had a full meal and there is no place in your tummy for more? Surely you would say, "Thank you, I'm full." Similarly, these elements cannot take any more electrons. A fully occupied valence shell is the most stable electronic configuration of an element. Such a configuration is called an octet configuration. All inert gas elements have an octet configuration. Hence, they do not react with other elements. Why are other elements reactive? Let us consider the electronic configuration of elements sodium and magnesium, which belong to the first and second groups of the third period. Recall that valency of an element is given by the number of electrons lost or gained during its reaction with other elements. It is also called combining capacity. What do you observe here? Sodium can attain octet configuration by losing 1 electron and magnesium can do so by losing 2 electrons. This can be done by reaction with other elements which are able to take the electrons. Can you give examples of elements that gain electrons to complete the octet? Therefore, elements other than inert gases are reactive and form compounds with other elements. Sodium is said to have valency 1 and magnesium has valency 2. Try to work out the valency of the elements in the second period. To find the valency, follow these simple rules. Determine the number of valence electrons. If it is less than 4, then valency is equal to number of valence electrons. If it is greater than 4, valency is equal to 8 minus number of valence electrons. For example, in chlorine, number of valence electrons is equal to 7. So, valency is equal to 8 minus 7, which is 1. You will see the following pattern. If the number of valence electrons is greater than 4, the elements accept electrons to complete their octet. Work out the valencies of period 3 elements. The pattern of the valencies remains the same for this period also. Recall that you have learnt in the previous lesson that elements in the same group have the same number of valence electrons. What do you say about the valency elements in the same group? Do you think they have the same valency or different valencies? You have already worked out the electronic configurations of lithium, sodium, and potassium. Figure out the valencies of these elements in the same group. You will see that all elements in this group have valency 1. The elements belonging to the same group have the same valency. Here is a pattern seen in the valencies of elements when we move across a period. When we move down a group, we see that all the elements have the same valency. Recall Mendeleev's thought process. In the modern periodic table, we saw that the valency of all the elements in a group are the same. Mendeleev chose the formula of compounds formed by the elements in deciding the position of the elements. Do you think this was correct? Is there any relationship between valency of element and chemical formula of compounds they form? The valency of the compound decides the number of bonds and type of the bond formed between the elements. Due to this, the elements with same valency form compounds having same formula. Therefore, Mendeleev was right. Take a look at this. My height is 140 centimeters. My height is 145 centimeters. What can you say about this? We can compare the tallness by measuring the height. Height is measured in centimeters. Similarly, many properties of an element depend on the size of an atom, and there is a need to have an idea about the sizes of atoms of different elements. Defining the concept of atomic size. How would you compare the sizes of atoms? How do you define atomic size? The atomic size refers to the atomic radius, which is defined as the distance between the center of the nucleus to the outermost occupied shell of electrons in an isolated atom. What is the unit used to measure atomic radius? Atomic radius is most conveniently expressed in picometers, where 1 pm is equal to 10 to the power of minus 12 meters. How does the atomic size vary in the periodic table? How does the atomic radius vary as we move along a period from left to right in the modern periodic table? A. It should increase in a regular manner because the atomic number increases. B. It should remain the same because we know that the electrons are added to the same shell till the end of the period. Which answer would you choose? The probability of choosing the two answers is 50-50 because the reasons are equally justified. Is there any pattern for this property as we move across the period or down a group? We shall try to find answers to these questions. Take a look at this. Here is a pictorial representation of the variation in atomic size along a period and down a group. What do you observe? The atomic size decreases as we move from left to right across a period. The atomic size increases as we move down a group. This means that both the options are wrong. Why does the atomic size decrease across a period and increase down a group? Let us take a look at the electronic configurations of elements of second period. What do you observe? As we move across the period, we see that there is an increase in the atomic number by 1 unit. With increase in the atomic number, the number of electrons also increases by 1. This new electron will enter into the same outer shell as we have already discussed. Recall that atomic number is equal to number of protons, which is equal to number of electrons in a neutral atom. Along with the increase in the number of electrons, the number of positively charged protons within the nucleus should also increase. This increases the positive charge on the nucleus, due to which the nucleus exerts a greater attractive force on the electrons and pulls the electrons towards itself. The shell shrinks and the atomic radius decreases. Now, what happens when we move down a group? When we move down a group, the electron enters a new shell which has a bigger radius. The distance between the nucleus and the electrons is increased. Therefore, the atomic size increases in spite of increase in the nuclear charge. The atomic size decreases as we move across the period and increases as we move down a group.